Welcome to the Ontario High School video podcast. We're still in the area of acid-base fundamentals. We are at part 9A, dealing with titration. There will probably be 3 to 4 parts here, so stay tuned. We are going to look first at the titration of a weak acid with a strong base. Welcome. A couple of definitions up front. An acid-base titration is when you add base to an acid or acid to a base until the equivalence point is reached. The equivalence point is where the number of moles of acid exactly equals the number of moles of base. Here's where things get interesting with the equivalence point pH. When you titrate a strong acid versus a strong base, the pH at the equivalence point will always be 7. Now, you know the strong acids, you had to memorize them. There are 7 of them. And you know the strong bases. Those also you had to memorize. But when you titrate a weak acid and a strong base, the pH is going to be greater than 7 because when you reach the equivalence point, at that point, all of the acid has been converted to the salt of a weak acid, which is a conjugate base. It's a weak base, but it's going to cause the pH at the equivalence point to be greater than 7. For a weak base titrated with a strong acid, the pH will be less than 7 because the salt of the weak base is a weak acid. Thus, you have a pH less than 7. So keep that in mind as we begin this journey, and we'll be good to go. Let's look at a sample problem to demonstrate the titration of a weak acid versus a strong base. We have a 100 milliliter sample of a 0.150 mole per liter HNO2 or nitrous acid. Our pKa is 3.35, and this is titrated with a 0.300 mole per liter sodium hydroxide solution. We want to determine the pH of the solution after the following quantities of base have been added to the solution. First before any, and then at 25, 49.5, 50, and 55 milliliters. So that's our goal for today. Because of the magnitude of this problem, we'll be solving parts A and B, meaning the pH where none of the base has been added, and then where 25 milliliters of the base has been added in this particular podcast. We'll take on C, D, and E in subsequent podcasts, but for right now we're just going to look at A and B. So at part A we have 0 milliliters of the base added, so it's the pH really before the titration begins. In order to do this, we first need to find the Ka value for the acid. And we know that the pKa is equal to the negative log of the Ka value. So to find the Ka value, we just take 10 to the negative pKa. So 10 to the negative 3.35 gives us a Ka value of 4.47 times 10 to the negative fourth. Next, we're going to set up an ice chart and calculate the pH for the solution based on the concentration of H3O plus as a result of the weak acid donating a proton to water molecules. Here's our ice chart, and here's where the critical part of acid-base equilibrium is to be able to write the reaction of the weak acid or the weak base. A weak acid will act as a Bronsted-Lowry acid, meaning it will act as a proton donor. It will give an H plus or ionize an H plus ion that will be picked up by the water to form, by a water molecule to form H3O plus, which is known as the hydronium ion. So our initial concentration of HNO2 is 0.150 moles per liter. The water is in the reaction equation, but because it's a pure liquid, its concentration never changes, and therefore it's not a part of the equilibrium that we have to account for mathematically. Our initial NO2 minus and H3O plus is 0 and 0 respectively. Our change, the change in the HNO2 will be by an amount of minus x, and the change for NO2 minus and for H3O plus will be plus x and plus x respectively. At equilibrium, the concentration of HNO2 will be 0.150 minus x, and the concentration of NO2 minus and H3O plus will be X and X respectively. And one of the first things we want to do is check to see if the X has any type of effect on the initial concentration of HNO2, because with weak acids they usually ionize such a small amount that the initial concentration and final concentrations are so close that in terms of significant figures they remain the same. So to do that, we take the Ka value and divide it by the concentration of the nitrous acid HNO2 initially. We multiply that by 100, and so we take 4.47 times 10 to the negative fourth divided by 0.150 times 100, and we get 0.298%. Now, different people have different views on how big a difference it has to be for you to be able to drop out the X or to keep it. Generally, if that ratio is less than 1%, from my point of view, you can drop the X out of the expression and just leave the equilibrium concentration of HNO2 as 0.150 moles per liter. Want to just show you again mathematically the justification for why we can drop the X out of the 0.150 minus X, and there's the calculation. Since it's very, very small, we will leave the equilibrium concentration of nitrous acid as 0.150 moles per liter. We're now ready to write our equilibrium concentration expression and solve for the concentration of H3O plus, which is going to be the key to our initial pH. So we know that the Ka is equal to the concentration of NO2 minus times the concentration of H3O plus divided by the concentration of HNO2. Since we fill in from the ice chart the concentrations, we have X times X on top divided by 0.150 minus X, except we can simplify the bottom and take this to X squared divided by 0.150. Our X, which is our H3O plus, then would be equal to the square root of the product of our Ka times the initial concentration, the concentration at equilibrium of the HNO2, which is 0.150. And so the concentration of H3O plus would be equal to the square root of the product of 4.47 times 10 to the negative fourth times 0.150. And when we do that, we get a value of 0.00819 moles per liter H3O plus. Now that we've found the value of the hydronium ion concentration, the H3O plus, we can then find the pH by taking the negative log of the H3O plus concentration, which would be the negative log of 0.00819, which would leave us with a pH of 2.087. When you're preparing a curve to represent the pH points versus the volume of the titrant or the NaOH added, this would be your initial pH point. At 0 milliliters of the hydroxide ion solution added, the pH would be 2.087. Next, let's look at Part B of this problem. Part B of the problem is to find the pH when 25.00 milliliters of the 0.3 mole per liter NaOH is added to 100 milliliters of the 0.150 mole per liter HNO2 or nitrous acid. We're going to do this in a short way, and the way that we'll do this is to first determine the number of moles of hydroxide ion and HNO2 involved in the titration by multiplying the volume in liters times the concentration in moles per liter. Now, I had said before we're going to show you a long and a short way, and I'm showing you the short way now, and I have decided that I think the short way being the simpler way to solve for these, and it is a correct way of doing it, that we will leave it with just the short way on this podcast. So anything in terms of a long way, if you want to ask your instructor to show you the long way, that would be fine. But I think the short way will be the way to go in terms of simplicity of problem solving. So continuing on, here we have the solution for moles of each of these. We take our volume in liters times the moles per liter of each of the substances we're dealing with here, the HNO2 and the OH minus. And when we do that, 0.1 liters times 0.150 moles per liter HNO2 divided by 1 liter gets us 0.00150 moles of HNO2. 0.025 liters of 0.3 moles of hydroxide ion per 1 liter gives us 0.0075 moles of hydroxide ion. Now that we know the number of moles of each of the HNO2 and the OH minus, we're going to set an ice chart up with mole values rather than concentration values. And the way that we are going to do that is to show this reaction, which is a neutralization reaction, and we're going to leave the sodium ion out of the reaction equation here. We want just the net ionic reaction. So we have HNO2 plus the hydroxide ion, OH minus, and we are forming NO2 minus, the nitrite ion, plus H2O. Our initial concentrations of the HNO2 is 0.0150 moles per liter. Of the hydroxide ion is 0.0075 moles per liter. Of the nitrite ion, which is the conjugate base of the nitrous acid, is 0, and the water is irrelevant. The change, all of the hydroxide ion is going to be used up in converting the nitrous acid to the nitrite ion, and so the change in the HNO2 quantity will be by 0.0075 moles minus 0.0075 moles. We're going to use all of the hydroxide ion up. It is the limiting reactant, so it also changes by minus 0.0075 moles. And the nitrite ion concentration increases by plus 0.0075 moles. So at equilibrium, we have 0.0075 moles of HNO2 present, we have 0 moles of the hydroxide ion present, and we have 0.0075 moles of the nitrite ion present. Now, right away, when you look at the number of moles of the HNO2 and the NO2 minus being equal at equilibrium, that should be a key to you that the pH will be really simple to find, because the total volume of the solution with the same number of moles of each of HNO2 and NO2 minus there, it means their concentrations are equal. And there's a real easy way to find pH when the concentrations of a weak acid and its conjugate base are present in the same number of moles per liter of the solution. So we'll take a look at that next. Looking again at the ice chart, we set it up in terms of number of moles rather than concentrations, and that will work for us. We do know the total volume of the solution. We know that there's 100 milliliters of the HNO2, and we know that 25 milliliters of the hydroxide ion solution, which contain 0.0075 moles of hydroxide ion, has been added. At this point, you have a choice. You're going to use Henderson-Hasselbalch. You can use the ratio of moles of NO2 minus over HNO2, or you can calculate the new concentrations for each of those, which would be 0.0075 moles of each divided by 0.125 liters to find the new concentration. Either way, the ratio will be equal to 1, and because the Henderson-Hasselbalch equation depends upon the log of the ratio of the concentrations, we know that the log of 1 is 0, which makes finding the pH very easy. So here's our Henderson-Hasselbalch equation. I happen to use the ratio of the moles of the NO2 minus to moles of HNO2. You could have used the log of the concentrations of the NO2 minus to the HNO2, which would be 0.0075 moles divided by 0.125 liters, which would make the molarity of the NO2 minus and the HNO2 solutions 0.0600 moles per liter. Either way, that ratio is equal to 1, and the log of 1 is equal to 0. So at this point, pH is equal to pKa, which is 3.35. Now, if you're doing a graph of this titration, we've already put our initial pH at the 0 milliliters of the titrant added. At this point, at 25 milliliters of the hydroxide ion solution added, you would place a pH of 3.35 on the graph. So stay tuned for the next podcast, which will go into solving parts C, D, and E. It may take more than one additional podcast. We'll see how that goes. But we're very close to the end here. So this is the end of the part 9A of the acid-base fundamentals series here for AP Chemistry. This is also going to be used for the Chemistry 2 courses here at Ontario High School. But I want to leave you with a quote from Walker Percy, great Southern novelist. "The search is what anyone would undertake if he were not sunk in the everydayness of his own life. To become aware of the possibility of the search is to be onto something. Not to be onto something is to be in despair." I wish you well.